So now we're going to start chapter 4, the last section, part 3, and we're going to start this with section 4.6, the multiplication rule and independence. Now, let's talk a little bit about how we find intersection probabilities. So the way that we've been doing it is directly from the joint probability table. Remember, the intersection are the joint probabilities that are in the center right here. So here's our totals. And our totals. And our joint probabilities are in the middle here. These are one way that we find intersections. We literally take the intersection in order to find, say, this one. So the next way we can do is we can use what we call the multiplication rule. So let's say, for the sake of the argument, that we know the conditional probability and we know the probability of the given event. We can use the multiplication rule to find our intersection. Think about this. This is just a rewriting of the conditional probability formula. If I multiply both sides here by probability of B, these would cancel, and I would just end up with the probability of A intersection B is equal to the probability of A given B times the probability that B happens, which kind of makes sense, because if we say this is the probability that A happens if we know that B happens times the probability that B happened. So this is out of the times when B happened. So maybe if this happens 50% of the time and the probability of A given B is 25%, well, it's 25% of this 50%, which is 25% of 50%. So that's 12.5%. So that's the probability that they both happen at the same time. Or we can use independence. Now we're going to discuss this later. So note, I already said this, that this is just the conditional probability definition rearranged. So, sorry for the pause. Sometimes OneNote, that's the program that I'm using, likes to act a little bit crazy. Okay, so let's do this example. This is the class standing example. So let's say that in a class, maybe it's a statistics 252 class, we have 36 students. In this class, 16 are freshmen, 10 are sophomore level, 6 are junior level, and 4 are at the senior level. And let's say that 2 students are selected at random, one at a time. So we want A, the probability that the first one is a sophomore and the second one is a senior. So we want the probability that the first one is a sophomore. So that's this S1. Intersection, the second one is a senior. Now, I can do a couple of things here. I can say, well, this is going to be equal to the probability that the first one's a senior, the second one's a senior, given that the first one was a sophomore, times the probability one was a sophomore. Because think about it, every single time we take one, it changes the probability because we're sampling without replacement. So as soon as I take this person out, this sophomore, that changes the probability. Because this probability of taking a senior the first time is 4 out of 36. But if I've already taken one of these sophomores out, it's 4 out of 35. So I can look at this. I know what this conditional probability is. I know what the probability of getting a senior second if I got a sophomore first, because I still have 4 seniors, but now this is 9, so this is 35. So now I have 4 out of 35. And I know what the probability of getting a sophomore the first time is, because it's 10 out of 36, or 5 out of 18. And we can just use this multiplication rule. So the probability, should be intersection, the probability that S1 intersection SR2, I can multiply these together. 5 over 18 times 4 over 35. I did some canceling. Divide this by 2, I get 9. Divide this by 2, I get 2. Divide this by 5, I get 1. Divide this by 5, I got 7. And I end up with 2 out of 63. So let's take a look at part B. What is the probability that both of them are freshmen? So we want the probability freshman 1 intersection freshman 2. So they both have to be freshmen. So this can be broken up. I know what the probability of freshman being second if I'm given that a freshman was chosen first, and I know the probability of a freshman being chosen first. So I can go, okay, the freshman chosen first was 16 out of 36. The probability of a freshman chosen second, given that a freshman was chosen first. Now, if we look at this, well, if a freshman was chosen first, I only have 15 of these guys out of 35. So that's 15 now out of 35. Let's see what we've got here. That's 3 out of 7 times 4 out of 9. I just divided both of those by 4. And we have 12 over 63. Oh, I could have done that farther. Could have done these two also. And ended up with 4 out of 21. So there's the answer to that one. So now for part C, the probability that they are a freshman and a junior. Okay, now things get really interesting, because now what I need is the probability that the first is a freshman and the second is a junior, or the probability that the first was a junior and the second is a freshman. But let me ask you a question. Are these two things mutually exclusive? Think about that. The freshman first and junior second, junior first and freshman second. Can these two things happen at the same time? So they're not. They can't happen at the same time. Oops. Right on it. Sorry, little glitch there. So they cannot happen at the same time. So it cannot happen together. So these two are mutually exclusive. When they're mutually exclusive, remember, or probabilities are unions, and when unions are mutually exclusive, we can add them. So what we really need to do is add the probability of F1 intersection with J2 plus the probability of J1 intersection with F2. So that we can also break down farther is simply, whoops, I know it's written down there, but I want to do this together. So this is the probability of J2, so junior is second, given that a freshman was first, times the probability that a freshman was first, plus the probability that a freshman was second, given that a junior was first, times the probability that a junior was first. So here, what's the probability that a freshman was first? Well, we know that. That's 16 out of 36. The junior, given that we have a freshman first. So if this freshman got taken first, now there's 15 of these, 35 of these, but now the juniors have 6. So that's 6 out of 35. Plus, now the probability there was a junior first was 6 out of 36. And the probability that there's a freshman second, given that there was a junior first. So let's change the parameters a little bit. So the junior was first, so now there's only 5 juniors, 35, but we want 16. Now look at this. This is really interesting. You'll notice something. These two are the same probabilities because we have 6 and 16 at the top. because here we didn't change the tops, but we just come out of 35 now. Isn't that interesting? So even though we're doing this without replacement, this just becomes 2 times 16 over 35 times 6 over 36, because we're adding the same thing to itself. So let's see, these become 1 over 6. We can do the 6 with the 16, 8, and 3. And it looks like we have 16 over 35 times 3 is 105, I believe. And that would be our answer. 16 out of 105. Or 6 out of 105 and 16 out of 105, which is the same thing that I got down here. So you can see these were the same answers that we got. Okay, so now let's talk a little bit about online shopping. That's always fun. So 52% of the US population is women. Maybe. It changes all the time. 32% of women shop online at least once a week. What is the probability that a person selected at random will be a woman who shops online at least once a week? So this, when I see of women, I automatically think conditional probability. So probability someone is female, 52.52. Probability someone shops online, given that they're a female, 0.32. So the probability that it is a female who shops online, the person selected at random. So now we're taking the entire population, so we're looking at an intersection, is, well, 32% of the 52% of people that are women. Multiply these together, and you get 16.64% of the population. So now let's talk a little bit. I promised you guys I would talk a little bit about independence. Now, these things all mean the same thing. The incidence of one event does not change the probability of the other. So this is very different than our class standing example, because as soon as we took one person out, it changed the probability. However, if you think, if we were talking about millions of people, and we looked at 5 million out of, say, 36 million, and then let's say the first one was a freshman. So let's say these are all, we have 5 million freshmen in the world out of 36 million students. Well, think about what that's going to be. That's just going to be, the next probability is going to be this. Which is almost exactly the same thing. It is so close that we don't worry about when we draw when we draw without replacement from millions of people or from any large, extremely large sample. So, because the probabilities do not change enough to make a difference. It's negligible. So, but we have true independence in that if we roll 2 dice, each dice is independent, right? If I flip a coin twice, each flip is independent. And there's many more things that just run independently of each other. I've done the test for gender and handedness. Those are fairly independent. We can't really prove it using what we have already, but later on in the class, we will actually show you a test for independence that we have given some data. So if something is independent, that means the probability of A, given that B happened, is the same as the probability of A given that B complement happens, because it doesn't matter if B happens or not, with just the probability of A, because B does not affect A. It does not matter. It doesn't know. The second coin flip doesn't know what you got the first time. It's still 50-50. And that means that the probability of A intersection B, well, if you think probability given B, because think about this would be the probability of A given B times the probability of B. Well, if this is equal to just the probability of A, then you just multiply them. So you can find intersections by multiplying probabilities only when A and B are independent. Now, we assume independence quite often, you'll see throughout the class, when it's what we call pseudo-independent, when we're, of course, taking a sample without replacement from a large population. So consider these two events: a 3 on one die and an even number on a second die. So what's the probability of this happening? What's the probability of both of these happening at the same time? You roll two die, one has a 3 and the other one is an even number. Well, all you have to do is multiply those probabilities. So the probability of the 3 is 1/6. The probability of an even number is 1/2. So we end up with 1/12, which kind of makes sense, because it can, if you list all of the possible ways that can happen, that kind of works. Because you can have a 3 and 2, a 3 and 4, or a 3 and 6. There's only 3 ways that can happen out of the 36 dice rolls that are possible with 2 die. So therefore, that becomes 1/12. But this is a much more concise way to do it. So let's think about these machines. So we have machine A. Machine A has a breakdown rate of 5%. Machine B has a breakdown rate of 2%. What is the probability they are both broken down at the same time? Now, keep in mind, they have nothing to do with each other. These machines run separately. Okay, so what is the probability that both machines are out? Well, the probability that machine A is broken is 0.05. The probability that machine B is broken is 0.02. So the probability that they're both broken is just 0.05 times 0.02, which is 0.0010, or 0.001. So we could also do this in a percentage, 0.1% of the time. So 0.1% of the time, both machines are broken. So that's not very likely for both machines to be down. And I wrote this down here because I also wanted to point out that we could have a whole lot of independent events that can be multiplied together. So if we can say roll 3 die, roll 4 die, roll 5 die, and it really does not matter. So they're completely independent. And we can just multiply all their probabilities. So if you think about rolling 3 5s, if you're playing bunco or something, so that would be 1/6 times 1/6 times 1/6, since each one is 1/216, since each one is independent. Rolling 3 5s. Okay, so let's take a look at what we have here. So this is a problem with injured Americans. So the National Center for Health Statistics collects data, and we have a contingency table. So we want to find the probability of C1. That is the probability that somebody gets injured at work. So this is a contingency table. So we have to take the total number of people that got injured at work, 9.3 million over 61.4 million, and we get 0.151 million, or probably not million, I'm sorry, 0.151, or 15.1% of people get injured at work. People who get injured at work. Occur at work. So what is find the probability that C1 given S2? Okay, so now we're given that the person is a female. So out of all the females, so now we don't even care about males anymore. We don't care about the totals. We're only looking out of the females. So out of all the females, the 25.8 million females, 1.3 of them were injured at work. That's 0.05. So, or 5% of female, 5% of female injuries occur at work. So out of the females, only 5% of them get injured at work. Now, the question is, are these two independent? Well, the answer is no. And this is going to come up on a test. So I really want you guys to know how to do this. So the probability of C1 given S2 is not equal to the probability of C1. These are not the same, because we have, it is more likely, it appears, to be injured at work if you're a man than a woman. So a higher proportion of men get injured at work than women. So these two are not independent. So your gender influences where you get hurt. Okay. So is the event that an injured person is male independent of that the injured person was hurt at home? Now we can also do this from the male perspective. So we can look at this in a couple different ways. The one that I've done here is the same way we did the other one. So what is the probability someone is male? Okay. Probability someone is male is 35.6 out of the total. So 58% of the people were male. So the probability somebody was injured, or somebody was male, given that they're injured at home. Somebody was male, so we're given that they're injured at home. We don't care about these anymore. So that's 9.8 out of 21.4. That's 0.458. These are non-independent because the probability that S1 given C2 is not equal to S1. Now, another way to prove this would have also been is the probability of S1 intersection C2 equal to the probability of S1 times the probability of C2. Well, let's find out. So the probability of S1 and C2 is, let's see, we've got, that's 9.8, because remember, it's the intersection, 9.8 out of the total. Is that equal to probability of S1 is 0.58. Probability of C2 is 21.4 over 61.4. And let's get our calculator out here. And let's see, which clears every time I get it. 9.8 divided by 61.4. This one is 0.1596. That's equal to 0.58 times 21.4 divided by 61.4, 0.202. This is not equal. So therefore, they are not independent. So where you get injured is dependent upon your gender and vice versa. Okay, so one of the things that a lot of folks have problems with in the class is independent versus mutually exclusive events. So when we're independent, the events have nothing to do with each other. One happening doesn't have anything to do with the other one happening. And it doesn't prevent the other because it doesn't do anything. And we end up with the intersection is the two of them multiplied together. So they can happen at the same time. And in fact, their probabilities can multiply to equal that. So in mutually exclusive, events can never happen together. One of them prevents the other. The intersection is 0. One makes the other one not happen. So I think of this as 2 dice. Think of this as 1 die. Okay, so 2 dice being a 3 and a 4, or 1 die being a 3 and a 4. 2 dice being a 3 and a 4 is independent. 1 dice being a 3 and a 4 at the same time? Not possible. So it's mutually exclusive. They can't happen together. Okay, so I'm going to jump into Bayes' rule a little bit. Some of this is kind of weird, but it's not too bad. So let's talk a little bit about the law of total probability. This thing is so important.